And so you've been working in industry for a while, or what have you been doing?
Yeah, so I did some research as well as look out for jobs, but then COVID happened and I had to go back to India during COVID because of the work visa situations and hiring freeze and everything. But then in India, I worked for the industry, and then while working, I got the advertisement, and then I applied, and somehow I ended up here.
Let me see your equation underneath Michigan Tech. What does it say?
It just says engineering, but
engineering, yeah. D/2. Yeah, that's good. That's good. Yeah. And what t-shirt are you wearing? Shelbie?
Yeah, I have a Michigan Tech
Husky shirt. Very good. I feel like I should.
I visited.
I know.
I know, Anna. You got the flag in the background. I've got my flag over.
That's true. Yeah. We all logoed up in some way. Yeah.
That's good. That's good.
So I see in the comments that someone suggested Musher's wax. Dan suggested Musher's wax for dog feet. So I'm gonna write it down.
There you go.
Well, I was thinking there's got to be a product. I was thinking you might just try WD-40, but then the dog will lick it off, or like something bad will happen if you use WD-40. But that sounds much better. There's got to be a product for this, right?
Yeah, we don't need it often here, but I do have a dog that's basically a cotton ball. So.
Oh, those. My daughter had, I call it a snickerdoodle, but I know that's the wrong word. She had one of them, and it was like a spaz. It never held still. It wanted to be in the bed, it was just leaping and jumping, and and then it would escape, and then you'd have this escaped snickerdoodle, and you had to trap it. You had to pretend that you were going somewhere in a car in order to get it in the car, and then you had it trapped. I mean, it was just. Honestly,
was it a bigger dog or like a smaller?
It was a big one. Yeah, no, the dog. Yeah, it was like it had. Big. Yeah, no, it was.
It's surprising how big the normal size ones are. I have a family member that has the normal size, and they're big, and they don't know they're big. They're just all over the place.
Isn't that funny how dogs are like that? They just don't know. Yeah.
They're knocking stuff over.
Yeah.
So Anna, I don't know if I told you, my husband is doing a cross-country bike ride. So he's doing he's on a bicycle. When I say bike ride, he's on a bicycle with panniers and camping. And anyway, he's hit the part. He's now in Louisiana. He left Florida, and he has now been attacked by several dogs, and he has had to deploy his pepper spray. So he put in his blog about some pit bull mix that's not going to be tasting pepper for the next week or two, because he had to hit it in the face, and so he's now riding with one glove on and one glove off, so he can quickly deploy the pepper spray.
It's scary. I mean, most dogs are great, but
it's actually frightening. When I've only had one dog come after me, and that's fine. You can get off your bike and you use your bike as a shield, and finally the owner comes out if you're lucky, but. If you have two dogs, that just doesn't work anymore, because one's going to go around and bite your ankles,
True enough. So he must be southern U.S. right now, or?
He's in Louisiana.
You said Louisiana. Yeah. Okay.
Yeah, he's in a parish. He's got a party, I think, for Mardi Gras now.
Yeah, well timed.
Yep. All right. Let me start sharing my screen. This is always a process for me. I am so excited about this evening. I have been wanting to hear about your work for a long time.
Yay.
All right. Can you see my screen?
Yes, we see all
kinds of stuff there.
All kinds of stuff.
Draft Senate policy. All right. So let me now go to first slide. Woohoo! All right. Well, we are ready for an on-time start. Welcome to I've lost track of what episode we are, but we are in the middle of season 7 of Husky Bites, which is a Michigan Technological University free Zoom webinar that we later then post to make available via YouTube. These are, we're always trying to learn something new, and we hope you learned something new this evening. My name is Janet Callahan. My role at Michigan Tech is that I am the Dean of the College of Engineering, and I just want to welcome everybody here. So this is the spring menu. As I said, it's season 7, so we're about midway through, or exactly midway through, possibly. We're going to be learning about solar energy in cold climates. We will meet one more time on February 27th. And then, so Echo, whenever she hears my voice, she comes and says hi. So she gets to be on camera. There she is. Yeah, that's Echo. Abby's down at my feet. So we'll be talking about money matters. This will be a College of Business focused talk. And then we will have spring break and we will actually not meet. And then we have 4 more meetings in a row. Just a couple of updates. First of all, it's snowing here. It's not snowing heavily, but it's snowing. And we do expect some accumulation on Thursday. So I'll have to let you know next week how that happened. We're at 167 3/4 of an inch to date, which is not very much if you ask my dogs. They love the snow. I want to thank everybody who gave. And if you didn't give, it's never too late to give. But over $1,289,142 was given across about 1,240 some odd gifts. And I know some gifts came in early and they're probably not included in the total because they're adding it all together. So I just wanted to thank everybody. And I also wanted to point out the website. And Sue, if you can drop that in the chat, that URL. So there's this really fascinating webcam site where you can see the broomball cams, the black rink, and the, I don't know if you know about this, but I didn't know about this. And then you can see the campus aerial. You can see, these are all live. This is Husky Plaza. This is mid-campus Walker Lawn. So this, if you're ever interested in seeing what it looks like here on campus, you can even monitor the construction of our HSTEM complex, which should be open by this time next year. So I wanted you guys to know about that if you didn't already. And let's see. I wanted to shout out about the up next. Dean Johnson is going to be the featured speaker with students as the co-hosts, and they're going to be talking about the Applied Portfolio Management Program, wherein they invest real money and are doing pretty well relative to the portfolio. And so I hope you'll join us. And finally, thank you, everybody. I want to remind you, if you want to ask questions, what you want to do is type them in the Q&A. And then we will read them off later on. The chat does not work. We can chat at you, but you cannot chat back. Sorry for that. So with that, I'm going to, are you still seeing slides from me, you guys?
Yes.
All right, I'm going to attempt to stop sharing. I'm not sure how to do that anymore. So I've lost my field of view. I don't know. All right.
Yep.
Did I stop sharing?
You did. Yep. Excellent.
All right. So Anna, why don't you start sharing, and I'll do a brief introduction of you, and then I'll lead it to you to take it from here. So this evening, we have the great pleasure of having Dr. Anna Dyreson, who is a faculty member in mechanical engineering mechanics. This is her 3rd year as a faculty member here. Anna earned her Bachelor of Science in Engineering Mechanics from University of Wisconsin-Madison and her PhD there as well. And in between, she earned a master's at Arizona State University out west. Anna was raised in Wisconsin, in Portage, Wisconsin, which is in South Central, on a farm with 3 sisters. So I have that in common with you. And she loves to bike, camp, and run. And I'm going to just keep it brief, and hopefully you'll say a little bit more about yourself. So Anna leads the Great Lakes Energy Group, which is her research group here at Michigan Tech. And we're going to be learning about impacts of snow on future high solar share power systems. And so take it from here, Anna.
Great. Thanks, Janet. Quick question back to you. One of my sisters is an engineer too, so we're 2 for 4. What about you and your sisters?
Oh, 1 for 4. I got it. We
1
got
for
a we got a nurse, a homemaker, and then a kind of a programmer business person. Sarah can do anything. She's the youngest. Yeah. So
yeah. Great. Well, I'm excited too to talk about solar PV in northern climates. I think Janet gave a more than sufficient introduction about me, but really have focused my work in Michigan Tech on energy transitions and getting more specific about the Great Lakes region because of my interest in that, because I grew up in Portage, which is indeed in the Great Lakes basin. So it is in the watershed of the Great Lakes. And I've always been drawn to this region. I'm really excited today to work with Ayush and Shelbie. It's always fun to highlight student work. And they're part of my larger team. Ayush is a returning student, so he did his master's at Michigan Tech and then spent some time looking at remote and hybrid renewable power systems. So kind of some cool background there before he came back for his PhD. And Shelbie is an online PhD student with me, who also spent some time in the industry at some electric power systems, some electric power utilities on the Western US. So both of them bring interesting perspective, and I'm happy to give them the spotlight today to share their research.
well, I want to interject because I know someone's going to ask the question. So we do have a remote offering of a PhD program in mechanical engineering, as well as in civil engineering here at Michigan Tech. So if we have anybody out there who would like to earn a PhD, feel free to send an email to engineering@mtu.edu, and we're happy to share more with you about how to do that.
Very good. So sort of the way we organize the talk today, I'll begin with an introduction and kind of a quick primer on solar so that we all have some shared background. And then I'll hand it over to Ayush to talk about his work on optimizing single axis tracking systems, and to Shelbie for her work on impact of snow shading on the grid overall. And a few words at the end from me on where research is headed from here. As by way of introduction, sort of where this comes from, as I said, I've focused my research more and more on the Great Lakes region. And in general, we'll look at the impacts of weather and climate change on future power systems. So as you think about energy systems transitioning, at the same time that weather and climate are changing, there are these two concurrent changes that really intersect. And you can imagine how extreme temperatures, changes in extreme weather and precipitation affect the generation, transmission, and use of electricity, and all of that's rapidly changing. So our goal is to focus on the Great Lakes region, because I argue that every region has its own characteristics. If we don't explore those in each unique region, we won't have the right solutions. We won't understand the drivers in each region. So what does that mean in the Great Lakes? Things like lake effect climate, right? Like lake effect snow, and just how the lakes affect our climate overall. Heating services being very important in northern climates. What does electrification mean for electrifying natural gas, for example, furnaces to electric heat pumps? Snow shading on solar PV is our focus today, but I've also got an undergraduate student looking at wind potential on the Great Lakes themselves. And then some themes in my research are around post-industrial sustainable redevelopment. So interest kind of in that space, weather and climate change and how power systems change leads us to the core of today's talk on snow shading on solar PV in general. As I said, I want to make sure we have some shared background for solar. My research through my master's degree and PhD has been on multiple technologies. Solar PV is on the left. Solar PV has an efficiency of somewhere 15 to 20%, and they're always pushing that higher. This is kind of probably what most folks are most familiar with, but I just want to give you a range of different technologies to think about. So PV, right, requires batteries, at least at large scale grid integration. We need batteries, and we produce electricity, which is a very useful output, but it is electricity, versus a flat plate collector, which is shown in the middle, a technology that was mature more than a couple of decades ago. But we are using that to collect solar radiation, some backing on the bottom and convective panels on the top to optimize the heat transfer and collect as much radiation with the fewest losses possible. Gives you an efficiency of around 80%, but what you produce is heated water, right? So you're getting heat out of those, which is useful in some applications, while not others. Concentrating solar on the right is where I focused my PhD, and that takes either mirrors or parabolic troughs that are shown here to collect sunlight on a point, or in this case, a line, and you generate thermal energy through that concentration of solar irradiation, but then you use a power cycle to convert it into electricity. The efficiencies on those are moving up as they generate higher and higher materials that can withstand higher temperatures, but still you're kind of in the 25% efficiency range. So they're just very different ways of collecting solar, the abundant solar radiation that we have. And we will focus on solar PV. And as I said, I think most folks are probably most familiar with that. But I wanted us to have that shared understanding. So kind of further in that, then within solar PV, you may be most familiar with residential scale PV, which is shown on the left, but there's sort of a whole scale range and scale of technologies from residential on the smallest to utility scale solar at the largest. Residential scale solar is also sometimes called distributed PV because you have these small distributed systems in neighborhoods and communities that aren't usually, or at least I should say historically, controlled by a central location. Versus on the right, you can imagine a utility scale solar farm like this, which is of the scale of like a coal power plant, or maybe even the larger ones, the scale of a nuclear power plant. And so those can be controlled from a central place, right? And maintenance can be standardized. And like anything, the cost per unit decreases with scale, right? And then in the middle, you have commercial systems that you might see on your home or office. This is actually a picture of the Sustainability Demonstration House PV system on campus here at Michigan Tech. So kind of those systems that are a little bigger than you would need for one home, but not so big that they're really a utility scale system. And we wanted to let you kind of give you that framing that we're focusing on utility scale systems, though actually, I mean, I think the findings of our work certainly apply to both, but as we think about our research, it's sort of on that larger scale. Further on that, I guess within utility scale systems, the photo I'm showing you on the right is fixed tilt system. So the general rule is that if you locate a system, you fix the system at the tilt angle equal to its latitude, you're going to get the optimal amount of solar input throughout the year. That's the way that they were historically done. It's the cheapest and simplest way to do it, but there are also systems that track on 1 or 2 axes to follow the sun and collect more energy throughout the day, but they become more expensive and there's more moving parts, right? So our work is on utility scale and further on single axis tracking. Ayush has some really cool videos, so I'll let him kind of fully describe that more, but single axis tracking systems essentially track the sun from east to west throughout the day. So we like to take breaks and get some interaction. The first poll question is shown on the screen. Think about what percentage of all solar capacity in the US is utility scale solar. I've just introduced you to distributed, commercial, and utility scale. So do you think that is A, 25%, B, between 25 and 50%, C, 50 to 75%, or more than 75%?
Remember, I warned you, our alumni are pretty darn savvy.
She said it would be hard to trick anyone, but let's see. Let's see, 111 responses in there.
Well, we have 163 attendees, so, and that's not counting households, because lots of people are joining us with a whole living room full of people. Well, people are thinking A, less than 25%.
People are thinking A, okay. So the answer is actually 65%. So of the solar capacity in the US that's been built throughout time, you know, everything from decades ago until now, the answer is 65% of that is utility scale. So even though we know like our day-to-day experience might be more with residential scale, utility scale, because it's built at such large scale, right? It's actually 65% of the capacity we have, and they're only expecting that to grow. While residential scale solar will grow and commercial will grow and utility scale solar will grow, we expect that utility scale solar will continue to be the dominant of the three.
And I misunderstood the question.
Fair enough. Okay. Tell me what, yeah.
No, it's good. It's good. So that's interesting. So of the solar that has been installed, 65% of it is utility scale. Got it.
Yeah. Yep. And we'll do some more later that get into kind of the grid penetration too, if folks are thinking about that. So. Very good. I'll close that out and link to sort of want to talk about why we're focusing on single axis trackers, and then talk about our research site before I hand it to Ayush to get into his work. So single axis trackers are even though they're mechanically more complex, they do, of course, improve the output of the system by tracking the sun throughout the day. And they're now have taken over the market, not completely, but they've nearly taken over the market in the US. And there's an image there from a recent market report on that from a Department of Energy lab. And so we think, if you're thinking about northern climates and what matters near the Great Lakes, you would think that single axis trackers should have some benefits, right? Because snow will build up on panels, but then as they move throughout the day, they should drop that snow. But that's actually not been really shown. We really don't know how well they drop snow, what times of day, what types of events. And that's why our research has become more focused on that. And I want to shout out to Array Technologies, who was an early partner of mine in research and recognized and agreed with the importance of this issue and partnered to provide a 33 kW single axis tracking system on campus here, which is used for a couple different research projects, but our work primarily for Ayush's project. And so that just, shows this is currently industry relevant, and we're really happy to have a partner like that. But where do we do this kind of work on Michigan Tech's campus? There is a new site north of campus at APS Labs, if anyone is familiar with the Advanced Power Systems Research Center up there. It's near the airport, and we have a MIRTC, as we call it, the Michigan Solar Regional Test Center, which is one of 5 throughout the US. So the map on the bottom right shows the 5 locations of the regional test centers, which are managed by Sandia National Labs. And the idea of those is they all have the world-class meteorological and irradiance instrumentation, and industry can come and use those to test their systems in different climates and then cross-compare between different sites if they choose to. And it's also available for folks like me to develop research projects. So that site is a really great resource that we have, and it's operated by the APS Labs folks, and it can continue to be expanded. So that's kind of an opportunity for more research. I guess the image on the top right isn't really needed for this crowd. When I usually talk about this, I point out, why do we have the test center here? You all know that we have lots of and predictable snowfall, but that was attractive to the DOE as they selected a location for this test center because they want to be able to compare different climates. And we all know that energy transitions are happening across the country. So our site is here for a reason. And we're excited to continue testing new technologies and how they perform in cold and snowy conditions here.
And so if you land at the Houghton Airport and you're driving out, before you hit the end of that, before you hit the main road, the APS is about halfway down on your left, and you'll see the solar array from the road. Mm-hmm. And it's new. It's been there it was installed during the pandemic.
Very good. So with that background, I think I'll hand it to Ayush so that he can talk in more detail about his research.
Hello, everyone. Thank you, Dr. Anna. So my name is Ayush. As mentioned, I am a second-year PhD student. The project title is we have to optimize the single axis tracker performance in northern climates. It's a part of a larger project which includes different studies. So without further ado, I will move on to a little bit of background knowledge that why this is important. So in the March of last year, we achieved the world overall achieved the first terawatt capacity of solar. So for example, if it took us all of the solar photovoltaic development in the history, all of the years we reached the first terawatt last year, probably 60 years of development. And then as far as climate change is concerned, if we want to mitigate the climate change, we would need almost 68 terawatt. And that's only solar PV. So you can see the amount of growth and the amount of solar panels we need, and the industry is growing almost at the rate of 250% year-on-year growth. So solar panels require space. So that's why we need to have studies in snow areas. For the tracker optimization, it is a 2-year project. The first year is we want to know how much snow on the single axis tracker is. So we want to develop a baseline measurement. And to do that, we have a sensor-based system, which can give us real-time data, at any time, how much snow is on those panels. And the second part is to develop the algorithms, since solar single axis trackers can move from east to west. So if there is snow, we want to develop a smart algorithm that can take in account of how much snow is on the panels and then shed snow. Like the idea is if the snow, the panels are maximum tilted, the snow might shed off. So that's the whole idea of research. So we are at the end of our first year, we are doing the baseline setup right now. And as mentioned, the project is donated by Array Technologies. They already build world-class single axis trackers, and it is funded by Sandia Lab through Department of Energy, Solar Energy Technologies Office. On the bottom, you can see the team, and on the right is how the array looks in snow. Next slide, please. This in general, I will give you a very quick idea of like how the sensor-based system is. So on both the edges, there are the images. So our focus on this point is how to measure snow on the panel surface. So on the top left corner is the laser-based sensors. So what laser-based sensor do is like it reflects a laser beam on the surface, and then that's the reference point. And if there is snow, then that laser travels faster, and then it calculates the amount of snow that is on the sensor. And then the radar, there is also on the bottom right, you can see something called pyranometers. And on the extreme right left corner is the ultrasonic base. So we are employing both the technologies, one to measure snow on the panels and the other to measure what is the snow on ground, to have a good idea of like what exactly is snow. And there is also a radar deployed that can measure what kind of snow it is. It is a wet snow, dry snow, rain, or sleet, and at what times the snow falls. And this can all be collaborated into an algorithm which can correlate. And we are also using image-based analysis. So a camera would always be mounting the percentage cover of snow on the panels, since to our advantage, panels are dark color and snow is light colored. So to employ image-based algorithm, it would be very easy. Next slide. So this slide actually shows how the design development to how we mounted like a laser sensor on the panels. On the top center, you can see how we made a custom rig to mount a laser sensor that can rotate with the panels. So fun fact about this is that this has never been attempted before in the industry, because these sensors are made to measure snow on a fixed ground. So everywhere we look, this is the first time we are trying it. So kind of like a novel approach. On the bottom left is the radar, how it is mounted like very high on a container. And the middle picture is how the pyranometers are mounted up and down. Since our panels are bifacial, bifacial means they can generate electricity from top as well as bottom. So we need to measure like how much solar irradiation is falling on them. And this is a quick video of like how, when I say laser sensor has to move with the panels. So this is how a single axis tracker moves. And if you can see the rig, which is fixed, this is how it rotates from left to right. So I thought like this was images tell a story better than words. So in the next.
So I want to just repeat something you mentioned, because it was news to me. So when you said bifacial, I think you said solar panels. So these are collecting energy off of the front face, which is facing the sun,
Yes.
and the back face, which is getting reflected sun off snow.
Yes.
The back side. And
Yes.
I don't know if you guys knew that was out there, but that's been out there for a few years now. It's pretty cool, I think.
Yes, and a fun fact is that with the global shortage of silicon material as a whole, the cost of monofacial and bifacial are now very competitive. So part of us getting a bifacial was because there was no monofacial available to buy. So we ended up being with the bifacial ones, which used to be very expensive now compared.
Well, and if monofacial, I'm making this up, if monofacial are 15% efficient bifacial, what do you get? Like 17% or something like that?
A little bit more, yeah.
Yes.
18. Okay, so it gets you a measurably more.
Yes.
I'm fascinated by that.
Yes. And if we can, for the next two, I will show you two video clips of like how actually snow collects on the panels and how they sheds, and that's our hypothesis. If we can get the first video.
Sure.
So
January 31st.
yes, January 31st video. So this is being calculated. This is being captured. So if you can see how so this is the morning time, and so the video is moving very fast, frame by frame. On the left, you can see how the angle of panels changes, and on the right, you can see how the generation is being captured. So you can see there is almost like a 4 to 5 inches like thick sheet of snow on the panels. So as the sun is moving, the trackers are moving left to right, and then they follow a control algorithm. When there is no sun, they go back to the normal position. In the next video, you will notice something very interesting. So now if we can move to the February 4th video.
This is really cool, Ayush. This is cool.
So this is a more cooler video in my terms. So this actually encapsulates what we are trying to achieve. So as we can see, this is the morning time. Sun is up. It's 11:30, and then the sun is going over above head. The panels are flat. Now it's almost the afternoon time. The panels are moving towards west, and then you will notice something. Oh, there it is. So you can see this is the whole idea behind. Like if we increase the tilt angle, the snow might shed off. So this happened naturally because of the generation, but our algorithm would do if it will measure the thickness of snow and then initiate the tilt by itself rather than just following sun. So this is like a whole day of video encapsulated in 40 seconds. So that is basically in crux the whole project is about.
So what you're trying to do is, or one of the things you might be trying to do is decide when your array should tilt in order to shed the snow because enough melt has taken place.
Yes, there are like multiple variables I used to call. Basically, it's not just like always you can, whenever there is snow, you can initiate the maximum tilt. There are losses in going to the maximum tilt because hey, if the sun is on west and you want to tilt on the east, you would lose electricity generation. So that's why we have to do a smart algorithm, we call it, to capture all the parameters like wind speed, snow, weather, overcast, and all these issues. So that's the idea. And
so how much, I mean, just give me, I'm sorry, I'm interrupting too much, but like when you've got that much snow on it,
yes,
how much reduced is the solar generation? Is it like from 15%, are you getting 3% or like?
So as of now, the hypothesis is if there is a layer of snow, if you can see any white on the panels, the front side is generating no electricity.
Oh, wow.
So the front side is almost generating zero, and you can see that in the generation curves in the videos too. So, but there are some other parameters, like there is some transivity. Snow is not like opaque, and that's what we want to capture. Like what thickness we can consider snow as fully opaque. Like is it like 1 centimeter of snow is like fully opaque, or like half centimeter is fully opaque? And this research study would actually be able to tell us, and we can actually tabulate all these results. And after that, I have a quick question, full question probably. So we have heard like snow causes all these losses, but I want to ask everyone if they think, is snow all bad, or like, is there any benefit of snow?
And so the question is, does snow have any advantage for solar PV generation? A, yes, B, no, C, I don't know. People are saying yes, they're guessing yes, overwhelmingly.
Well, if they have actually tried clearing snow off from their like residential snow panels, everybody thinks snow is bad for solar panels. It destroys structures, and so yeah, I guess like everybody says yes, but I guess like the reason being which is taught, if anyone has taken any of the solar course or any chapter on solar, the performance of solar PV actually increases with decreasing temperature. So yes, less temperature means higher efficiency. But there is another reason, which is called albedo. Albedo is the reflectivity of snow. And since snow is very white and highly reflective on the ground, actually we want the ground surface to be white than black or like green with grass. So on ground snow is good, on top of panel snow is bad.
Okay.
So in short, that was the answer. And congratulations, 87% who actually said yes. Thank you.
Great. Thanks, Ayush. I want to pass it to Shelbie to talk about impact of snow shading on grid operations.
All right, thanks. So I just wanted to quickly say that, as mentioned earlier, I'm actually an online PhD student. So I chose Michigan Tech because it's a highly regarded engineering school, but also it has allowed me to be a full-time university instructor and get my PhD at the same time. So I'm working with Dr. Anna in doing some research. So my research with Dr. Anna is it explores the impact of snow shading on grid operations. So it's a great jumping off point from Ayush, where you can see that when snow covers the panels, as said before, you could have almost no output or no output. And so on a broader scale in grid operations, how does that affect supplying enough electricity to the people who need it? So solar installations, they're increasing in cold weather states. And this is reflected in the table on the right side of the slide. So this data is from the Solar Market Insight Report. It's published by the Solar Energy Industries Association, and it shows the top 10 ranked states based on their annual installed solar capacity. It shows a comparison between 2020 and 2022. So you can see that warm weather states, they lock down the top 4 rankings in both years. However, states that fall in the top 20 for annual average snowfall are bolded, and they make a surprising appearance in as the years go on. So notice that New York, for example, moved from number 8 in the rank to number 5 between 2020 and 2022. And then Michigan actually moved from 27th, which you cannot see in this top 10 ranking, to number 10 in 2022. So that's pretty significant. So this increase in solar installations in snowy states can be due to market drivers such as falling cost of PV, government subsidies, high cost of electricity in some regions. So with this PV increase in snowy states, we may see a new challenge, and that is resource adequacy. So what is resource adequacy exactly? Well, resource adequacy basically means that the available electricity capacity can meet load requirements, or basically provide customers with the electricity that they need. So the widespread use of solar in these snowy states, it may create a larger dependence on solar energy generation. But then the question is, what about the snow? So when snow covers panels, it blocks the light to the panels and reduces their output, as we've mentioned before. So the fluctuation between no snow cover and significant snow cover on panels, it may make this resource adequacy challenging in a grid with higher PV concentrations in these snowy states. So our research focuses on including the impact of snow shading on high PV penetration grids. Next slide, please. So the question we'd like to answer is, how do energy resource managers ensure reliable electricity in snowy regions with growing solar installations? And so our objective is to simulate grid behavior with high amounts of utility solar installations during snow scenarios. So to reach our objective, we've broken down this process into 4 steps, and you can see those 4 steps on the bottom of this slide. So first, we need to analyze the relationship between snowy states and utility solar growth. So this was done to confirm the need for high PV grid simulations in snowy regions. It also provided insight into possible regions of interest. So our findings, we've already completed this step, our findings are going to be in a following slide in a minute. The second step is to collect adequate snow data. So finding adequate snow data depends on determining a region of interest, verifying if the data separates snow and rain, because snow covers the panels versus rain just rolling right off. Identifying appropriate temporal and spatial data resolution. So what's the time, what's the sampling rate of the snow depth, and then how close are the sample areas. Okay, so we're looking at that, and then considering if we need to include climate change and how we include climate change. The third step is to develop a coded snow shedding model at a power plant level. So basically trying to model or predict how snow will slide off of those panels. And you could kind of see how challenging that would be in the video that Ayush showed, where you have fixed panels in some areas, you have single axis tracking in others. So coming up with a code that will model that. So for this step, we need to consider the climate of the region of interest, the ambient temperature, the orientation of the panels, and the panel types. So this phase, it actually includes designing, writing, and testing a snow shedding code. And then the fourth and last step of our research is to incorporate the snow shedding model into a grid simulation. And this step, it will quantify the impact of snow behavior. Okay, go to the next slide, please. So this next slide is just a quick overview of where we're at in the 4 steps. So currently, we are collecting possible data sets that we will then use in our coded model. So it's spring 2023, that's kind of where we're at. And then we've actually completed step 1, analyzing the relationship between the snowy states and utility solar growth. And I'll show those results on the next slide. So in summer 2023, sorry.
I'm sorry.
So I was just going to mention really quick, summer 2023, we plan to do the snow shedding code, and then fall 2023, we'll try and introduce that into an actual grid simulation. So, okay, so next slide, thanks. Great. So to investigate the PV growth per state, projected PV growth per state, we used Reed's capacity planning model. And that allows us to look at how states are projected, utility projection of PV installations, what that will be like in 2050. So we chose 2 scenarios. We chose one scenario with a high demand for PV and more PV-friendly public policies. And then we chose a second scenario that represents kind of a mid-case business as usual scenario with the same PV demand and the same public policies that we currently have. So for both cases, we compared PV capacity from 2020 to the projected PV capacity in 2050, and Reed separates the data by state. So in figure 1 on this slide, or I'm sorry, figure A on this slide, annual average snowfall is on the y-axis, and compound annual growth rate from 2020 to 2050 is on the x-axis. So states that have a compound annual growth rate of utility solar above 5%, and also those that experience more than 40 inches of annual average snowfall, are marked in red. Those are those red dots. And some high snowfall states even see a 10% compound annual growth rate. So that is for the high PV scenario in Reed's. Now plot B next to it has a similar layout, except that data is from the mid-case business as usual scenario. And you can see that there are still 5 states marked in red. You see a few fall out of that above 5% compound annual growth rate, but there are some that don't move a whole lot, even in that mid case. And then figure C and D on the bottom, they provide a different perspective of the data that we collected. So these are bar graphs, and they show the utility PV capacity in 2020 versus what is projected in 2050. So 2020 is in the blue and 2050 is in the orange. You can see that the states follow the same trend between the high PV and mid case scenarios. However, less overall PV is added in 2050 in the mid case business as usual scenario, which would be expected. So basically these results, this step 1 of our process suggests that resource adequacy grid modeling for high utility PV cases will need to include the impact of snow to ensure reliable electricity in the future. And so with that, I'll hand it back to Dr. Anna.
Perfect. Thanks, Shelby.
Yeah.
We do have one more poll question, but we mostly wanted to wrap up and make sure we had time for Q&A. So we can launch that question. And while you're thinking of your other questions, we wanted to know what you think, what portion of new power plant capacity, this is only new power, built in 2021 came from utility scale solar. So same range as before, less than a quarter to 50%, 50 to 75%, or more than 75%. So what portion of new solar power plant capacity came from utility scale solar? So this is interesting and maybe a bit contrasting from our earlier one. Actually, again, the webinar attendees are really smart and they get the right answer. So it is B. It's 29% of new power plant capacity overall that is from utility scale solar. But when you look at all the new capacity built, 15% of it was distributed. So 29 plus 50, it means 45% of all new capacity was solar. And then on top of that, 25% was wind. And so it's, I like those statistics because it really shows the transformation, even though only 5% of our electricity around that comes from solar right now, this transformation is happening, right? So the new power plants that are being built are largely variable renewable sources. Good job, audience.
All right, so awesome.
Yeah, thanks everyone for your time. Happy to talk about my research. You know, shoot me an email, check out my website, but we can touch on some questions from the audience if there's anything.
Yep, and so Dr. Dyerson's email is just ADYRESON, Dyerson @mtu.edu. So there are a ton of questions out there, and I'm just gonna throw it at you to start handling them.
Sounds good. Yeah, and Shelbie and Ayush, feel free to look through the questions too and grab one if you would like.
So if you're going to answer it, click on answer live, and then after it's answered, click completed.
Okay, so I'll answer one. Oh, sorry, Ayush, go ahead if you've got one.
I am saying like I am been typing as much as I can for the answers that I know.
No, I told you not to.
Okay.
The questions are for answering in the group. So now you have to remember a question that you already answered.
Yeah, there are a lot.
I'll click on them. All right, so we got the answers about Musher's Wask and Vaseline and all right, this is a good one. So if you're at the 45 parallel, do you set your full solar panel at 45 degrees? Asked Steve. And Ayush said, yes.
Yes, so in simple languages, yes, that is called the tilt of the panel. So latitude equals the tilt to optimize the maximum output, but due to other issues like wind speed and structural framing, you would have to go for like something less. So for example, if you are at 60 degrees latitude, ideally you want a 60-degree panel, but wind might be another issue. So
okay. And the furthest north solar installation, is it in Red Deer, Alberta? Asked John. And Ayush knows of one as far as Alaska and Fairbanks and as low as Antarctica. So, all right. So then what about ice? You answered a lot of these, Ayush.
Yes, I
So
was.
Ken asks, what about ice? Lower Michigan is getting less snow, but more ice storms. All right, so tell us about ice, Ayush.
So yes, the ice is another unknown factor at this point when we are reading papers. So ice is considered as like so most people consider ice as like a transparent one, but for research purposes, it is considered opaque. But with our studies, we think like we would get some data for ice too, and then we can actually encapsulate like, okay, there is a 5 mm layer of ice and it only causes like 2% losses in energy generation. But as soon as solar panels start generating electricity, they heat up, and that causes further melting and snow shedding. So it is kind of unknown at this point for us.
All right, let's move to the open questions now.
I saw a cluster of questions that I think are related. Folks had ideas. Does it make sense to, is there ongoing research to make the surface more slippery to shed snow more easily, Larry asks. And another related idea was, what about heating panels at certain times, from Albert? And maybe some windmills, Steve asks, could some windmills be used to clear the panels? And so basically the answer is yes to those questions. And folks have looked at heating the panels in the past. And I even just this last weekend heard of the case of huge blowers being used to move the snow. But the question is like, that takes energy, right? Input. And so how much are you willing to pay? How much are you willing to waste your renewable electricity you just generated for moving the snow? And so heating the panels has not been found to be cost effective so far. Plus, as Ayush said, when you heat the panels, they're less effective. But yeah, all those, I guess I'm saying yes, those things would work. And the question is like, what is the most cost effective way to do this?
Yeah, I have seen a couple of vibration questions, like what if you vibrate the panels? So that was that idea comes intuitively to everyone in mind, like why don't you like employ like a vibrating motor or like a vibrating bed too? But it is a mechanical structure, and any mechanical engineering student would easily tell us that vibration causes more issues to the structural integrity than benefits, and also it takes energy. So we do not want to shake the whole bed in case there is a fatigue failure or fracture developed at some point. But yeah, that has been also been looked at, not for our group, but other research studies are being done.
I saw one question asking about residential and asking if we plan to investigate snow shedding on residential. And I don't do so much the shedding. I mean, I do it in a more a larger scale, modeling the grid. And so instead of coming up with ways to get the snow to slide off residential, but I was just going to touch on that and say that Dr. Anna and I have discussed, after looking at a utility scale grid model, meaning just doing the utility installations, then going further into residential. Residential is going to be a lot more difficult because there's significantly more variables involved. So, but I don't know if, as far as the snow shedding specifically, if Ayush, you're looking at anything like that for residential.
So employing single axis trackers in residential, I do not think that would be any benefit. But I have to look for it. I will look and then I can email back that answer.
So John wants to know where you got your t-shirt, Ayush.
Oh, this was being a student. I look out for the Friday sales on campus store. So this was on sale, and luckily I found one in my size. So yeah, $10 for this t-shirt is a very good deal, I think.
All right, and so the link to buy one has been posted in the chat. It's available at the bookstore. Okay, John?
Someone asked how long solar panels last, their expected life. So my understanding is at least 25 years. Anna, is that
roundabout there? Yeah.
right? Yeah. They were talking about their small lights in their garden because those
Okay.
are a little less high quality than, of course, the big installations. But yeah, the big ones, they last for quite a while.
Yeah, and there's some degradation, known degradation
Mhm.
of those systems. I think less than 1% per year, something like that, but it could vary between systems, and that would be, you need to factor that in, when you're looking at a 25-year life or something like that. Like, it won't perform like anything, right? It won't perform as well as it did on year one, but still pretty darn good.
The warranties are usually around, depending on what panel you get, they can be 25-year, maybe not 25-year output warranty, but a 25-year like hardware warranty, and they might have like a slightly different output warranty, but yeah.
There are some questions about things which I'm less knowledgeable about, the government policies specifically and the anti solar part. So I simply say we should not be able to answer those questions.
Well,
about
Anna might know the answer. Read one out.
So there was this one. How does your work get impacted by many anti-solar operations exist? Many signs along the roads in Michigan and Indiana say ban solar factories. So I simply do not know.
Yeah, that's a great and relevant question. It's kind of socioeconomic, right? Like what large scale manufacturing, like resistance to large scale manufacturing, environmental concerns. So I don't have one succinct answer for that, but nothing's a silver bullet, right? You have to account for the life cycle impacts of any technology you choose.
Yeah, as a climate enthusiast, so I just to, I guess, to shout out to United Nations COP. I have been to 2 COPs already, and I fall on the other end of spectrum that promotes climate change or climate mitigation policies. So if people are putting ban solar, then I would put, so those who support can show their support by putting solar panels. That's the straightaway answer, I would say.
So there's an interesting question from Becky. If you know it's going to snow, can you tell the panels to go vertical? And do you do that out there at our solar testing facility?
Do you want to take that, Ayush?
Oh yes, so that is actually called the snow prediction model, and the going vertical is very rare because of the mechanical limitations of the system. So our system can go negative 52 degrees to positive 52 degrees, but that actually is a part of the algorithm, like based on the sensors and weather sensors. If we have like 8 hours of snowfall predicted, we would actually go full tilt to not accumulate. But then comes another piece which I mentioned, wind speed. So if there is wind along with snow, you do not want vertical snow panels because they will just blow away. So you want them horizontal. So you see, this is like a very good optimization problem. Like, what do you focus more, your generation or your safety? So yeah, that's what our algorithm would do.
Yep.
Yeah, I guess I'll add to that to say that it depends on the manufacturer and like specifically how they design their trackers, because some of them they do have a high angle that's more stable. Some of them need to be flat in high wind events. So it just depends how they're designed. You can imagine the mechanisms to move those things throughout the day vary. So yeah, it depends, and hopefully with Ayush's work, we'll make a step towards some general recommendations about what makes sense.
And I'm seeing some questions. So, we covered a little bit of this in the talk, but so what I'm remembering is once there's about, like a third of an inch of snow or a centimeter of snow, they're not collecting power at that point, the panels. Would you say that's correct, Ayush?
So yes, but in our case, the panels are bifacial. So even if there is snow on top, they would be generating power from the reflected sunlight from the back, which is called diffuse sunlight. They would not be generating any power when there is no sunlight. That's surety.
right.
But
What about if it's a cloudy day and there's a little bit of snow on the top, but there's some light? Are they collecting power?
yes, it is called, they actually collect power every time, because overcast conditions, we have observed that it is not 0 watts being generated at any time. Even if it is overcast, if there is diffuse light, because we can see, so if we can see, there would be some sort of generation going on, and the whole point is we want to increase that some generation to more generation. So yes, even on cloudy and overcast days, they would generate very little. So it won't be 0, but it would be something, but not sufficient.
I
right,
think,
so good to
I
know.
think also to help maybe understand the impacts of shading, which can come from snow or trees or anything, is how solar panels actually work, like at least silicon solar panels, is you have light and then photons come in and they hit the silicon molecules, and then they dislodge electrons, and those electrons then flow in a circuit. And so if you don't have photons coming in and dislodging electrons, then you're not getting current, and then you're not getting power. So less light, less electrons, less current, less power. So if it's completely covered, you're not getting that current flow. I live in the Northwest and we have a lot of evergreen trees. And so when you install panels in like a, more of a foresty area, the shade does make a big difference.
Got it. All right, other questions to answer? I'm not monitoring what's been answered and what hasn't been answered because there's so many.
There's so many good questions. I'm having choosing.
Well, I mean, what I often do at around this time of when it's coming up in the hour, and I think I'm going to do this today, is I want to thank the audience for joining us, and I'm going to invite our team to stay on and answer more questions until about 7:15. But I just really want to thank our Husky Bites audience for joining us. I'm learning so much. I'm kind of very motivated to install solar here now. And it's which brings me a whole bunch more questions about economics. But thank you everybody for and thank you gosh, thank you Anna, thank you Shelbie, thank you Ayush. I wish I was back getting my PhD again. I would want to join Anna's group. I think this is a really exciting topic. So we're going to stay on, but we're going to call a halt to the recording so that we don't have a really, really long YouTube video out there, and we're going to keep answering questions. All right, you guys pick the questions.
Yeah.